Hey, Professor McStud here, and I'm talking about rate of change and slope. So along with the functions, we're talking about linear relationships. So a line is going to make a line as a constant rate of change, or also known as the slope. So if it's going to be linear, it's going to have a constant rate of change, which means it's going to increase by the same amount every single time. So here's a hot air balloon, and so the time is going up. This is going up by 1, and this goes up by 9. So this goes up by 1. This one, in order for it to be linear, has to go up by 9, and it does. Again, so in this table, it's got to go up by 1, and so if it goes up by 1, this one has to go up by 9, and it does. So that ends up being, so as the number of seconds increase by 1 second, so every single second, the height of the balloon increases by 9 more feet. So it's going to keep going up by 9 and by 9 and by 9. So it's very predictable. So you can see, we could say, after 60 seconds or 90 seconds, how high that balloon's going to go. And so that's kind of where we're going towards, is trying to get to that equation. So since the rate of change is constant, it's a linear relationship. And so it can still be a function, but it may not be a linear function or a linear relationship. The constant rate of change is 9 because it's going up by 9 feet for every 1 second. So you would divide that. That's where that gets at here. And then that means that the balloon is rising 9 feet per second. So let's look here. It says determine the relationship between the two quantities to see if the table is linear, and if it is, what's the constant rate of change. So here's how the best thing I think to show. So notice that this is going up by 1, and this is going up by 8. So start there. This is going up by 1. This one has to go up by 8. And does it? No, it does not. So therefore, it's not linear. Okay? It's not linear because we have an increase of 6 there. So, you could say, to kind of explain that. If it's not, then you need to explain. And so for 3 tables, it's going to be 24. And then for 2 tables, it was 18, which ends up being, if you kind of divide that, so for 2 tables, it was $9 per table. For 3 tables, it ends up being $8 per table. So a lot of times you'll see that, people will give you discounts or whatever for the more people you have, the less you pay per person. So that a lot of times is how that works out. So let's look at the next one, a greeting card. So we have, this is going up by 1. This is going up by $1.50. So total cost $1.50. I'm going to buy another, if I buy another card, so one more card, this should go up by $1.50. Does it? Yes, it does. So again, going up by 1 more card, this should go up by another $1.50, and it does. So no kind of special here. It's going up, so yes, it's linear. So again, here is kind of identifying, is it linear or not? If it is, what is the constant rate of change? Well, the constant rate of change is going to be 1.5 per card. And how did I get that? I divided 1.5, 0 here, divided by 1 here, and that's where I got this 1.5. So it's $1.50 for every card that you bought. Let's look at the next one here, donuts. So notice here, is this going up by 1s? It's not. So I need to kind of pay attention to that. It's going up by 2. So it's going up by 2, and this is going up by $3.25. Then it's going to go up by 2 again, and then it's going to go up by $3.25. Let's make sure that checks out. So if it goes up by 2 again, which it does, this has to go up by $3.25. So yes, it's linear. Yes, it's linear. So then I need to find my constant rate of change. What I'm going to do is I'm going to take this number here, $3.25, and I'm going to divide it by 2, because since I'm adding 2 dozen. So I want to find out how much it is per dozen. For 1 dozen, how much is that going to be? And so when we divide here, I get 1.625. Now we're talking about money here, so probably what that ends up being is like $1.63. And then once you, I mean, you get a little bit off because they start rounding up here. So if I went into the donut place and then I said, hey, I need a dozen donuts, it's going to be $1.63. But if I get 2 dozen, it's going to be $3.25. So that's kind of sort of how that works out, but it's still 1.625. That would be your unit rate. If we were looking at, I'm just saying that this is kind of sort of a rounded, because we're talking about money. Let's look at the time here and running. So in 15 minutes, they ran 2 miles. And so then in 30 minutes, they ran 4. So I add 15 minutes here, and I add 2 here. I add another 15 minutes here. I should add another 2 here, do I? No, I don't. So this makes this not linear. So what happened? Did they had to stop and get some water? Did they stop and see a friend and chit chat for a little bit? So or did they have to stop and walk, or what? Something happened and made that distance, less per for the 15 minutes. Longer time you run. That kind of thing. So this is not linear, and to go, and so you would want to explain there exactly as to why. So basically, this one is what kept it out. All right. So that's what I have: linear, nonlinear, constant rate of change. How much is it changing every single time? You're trying to find how much it is per one. So kind of sort of unit rate kind of ties into this, and we're going to talk about that and trying to tie all that together. So that's what I have for you for constant rate of change and slope.